Welcome back. Example 4 is really interesting. It says find the volume of the solid generated by revolving the region bounded by the following curves about the x-axis. Y equals the square root of x and y equals x squared. Figure 21 shows a little sketch of what that looks like. We'll talk about some of the details in just a moment. But I want to highlight a couple of things. One is that we're revolving this region about the x-axis. That's going to be very important to note. And so when we think about our cross sections, they're going to be circular in some sense. But the interesting thing about this example is it brings out something that we haven't seen before. If you think about taking one of these little cross-sectional areas right here. So remember how we took our region in 2D, kind of broke it up into some rectangles, and then we spun those rectangles about, and we ended up with these bright circular cylinders. Well, something interesting is going to happen because if we rotate this little piece right here, so this is representing like an infinitely thin rectangle, if we rotate that about the x-axis, we're not going to get a full filled-in circle. There's going to be some kind of hole in the middle. Because if you imagine this bottom part right here of this infinitely thin rectangle, which I'm just drawing as a line segment, this is never going to touch the x-axis. So as we're rotating around, there's going to be this hole in the middle. Let me draw that hole here. So something like that. Let me draw it slightly better. Skinnier at least. It doesn't look any different. Anyway, so there's not going to be anything inside that hole. Now on the top, we're also going to get sort of like another boundary of this cross section. In fact, something that you might even do that I recommend is to draw the whole region spun about 180 degrees across the x-axis or whatever axis you're spinning about, just so you can draw what it looks like on the other side. You might notice in some of the sometimes when I'm doing these problems, you might notice me doing that. And I haven't done it so far in these videos, but it would look something like this. There's the image of this leaf-looking region. If you spun it about the x-axis, this is what it would look like on the other side. It's kind of like a shadow of it on the other side after you rotate it 180 degrees. It just gives you something to draw the what do you call it? The cross section on. Okay. I should probably edit these videos, but oh well. My production value cost is, or budget is very low. All right. So what we have here that's really interesting is we have these circular cross sections, but they have holes in the middle. And that's because these rectangles didn't touch. They weren't right up against the axis of rotation. Or you can think this region wasn't laid out across the right along the axis of rotation. Previously, all of the regions that we looked at before, like for example this one right here, it was all flush along the y-axis. See how the region is kind of like sitting on the y-axis? So there was no place for a hole to open up when we rotated this region about the axis. This one was not a rotation, so that's not an example of what we're looking at. But this one is. See how the whole region is against the x-axis here, which is what we rotated about. So what we had was just filled in circles. They were completely filled in. Again, we're going to call those disks. But now, in example 4, we've got a hole that's opening up in the middle. Now the strategy is still going to be very similar. We're going to try to figure out what the area of these cross sections are. These holy circles or holy disks. And in fact, we're going to call these kind of shapes washers because they look kind of like the washers that you see. I'll have to try to find a washer in just a moment to show you. But they look like the washers that you see in engineering, like the things that you put to make the screws flush up and hold more tightly against the surface that you're screwing into. Not the washers like the washing machines. These are the engineering kind of washers. And so we're going to have cross sections that look like these washers. Let's take this washer and we'll put it flat on the page. Oh, not a bad circle. That was a worse circle. Let me try to draw that again. Okay, not too bad. So here we have the area that we're trying to find, the area of this washer. And so what we have is, let me actually use a different color, slightly different color. So we have this washer where we have the outer circle and this inner circle. Now how can we figure out, just generally speaking, what the area of the washer is? Well, if you think about it, one strategy is to take the area of the outer circle, right? Take the area of the outer circle, which would include everything inside of it. And that's going to be pi times this outer radius squared. So the distance from the center here to the outer radius, to the outer circle. So if you take that and then subtract out the area of the smaller circle, so pi times this inner radius squared, then that's going to leave you with the area of this ring right here, this washer. So that's going to be our strategy. First, figure out what the inner and the outer radii are, and then take the area of the outer circle minus the area of the inner circle, and that's going to leave us with the area in between. So those are the two things we need to figure out. This radius and this radius. Let's check out from the picture what those radii are. Let's start with the inner radius. So the inner radius is going to be the distance from the axis of rotation, which is at y equals 0, to this y value right here. So it's this little distance right here. And that's going to change depending on what x is. When x is over to the right, that's going to be a pretty big distance. When x is over to the left, that's going to be a small distance. So it depends on this curve right here, this bottom curve, the y equals x squared curve. So what you would do is you would take the y value up here, which is given by the formula x squared, minus the y value of the axis of rotation, which is just y equals 0, and that'll give you that vertical distance. And I just erased something accidentally. There it is. Never right-click. That erases things, apparently. So we can have that vertical distance, y equals x squared, that's the top y value, and then minus the bottom y value, which is y equals 0. So that gives you an inner radius of x squared. Let's write that over here, x squared. What about the outer radius? What would that be? If you said the square root of x, then that's correct. You'll take the y value up here along this curve, so that's given by the formula square root of x, minus, again, the y value of the axis of rotation, which is 0. And when you subtract them, you just get the square root of x. Okay, so that's looking pretty good. Now, to find the area of the washer, we'll take the area of the outer circle, which will be pi times the outer radius squared, minus, can't seem to write that 2. There it is. Minus pi times the inner radius squared. So that's the area of the inner circle. Again, the outer radius from our picture is the square root of x. Inner radius is going to be x squared. And we can simplify this to get pi x minus pi x to the 4th. And just for fun, we'll factor out a pi. Maybe not factor out the x, because in a moment we're going to be integrating these areas. Okay, so now we're going to take this and gently set it in. Our little formula for finding the volume of the solid that's made. Oops. And one thing we have to figure out is what our limits of integration are going to be. Where does our solid start and end? Now we're going to be integrating with respect to x, so we're going to figure out what x value does it start with and what x value does it end up at. Now from the picture we can tell that this is 0 to the first tick mark there, which is 1. But if you didn't know that, the way you could figure out where the region is pinched off over here is just to figure out the intersection point, just like we did in 6.1. So we set the two curves equal to each other, square root of x equals x squared, and then solve that equation. Let me just show you what that would look like up here. So if we had the square root of x equals x squared, we can square both sides. We can take one of the terms and move it to the other side and factor. And here you get x equals 0, which was actually the left end of our region, and then x equals 1, which is on the right side of the region. So this is just a little bit of work to show how you can get those intersection points. But the square root of x and x squared are pretty common functions, so it's good to know that they go through 0, 0, and 1, 1 anyway. Okay, so those are going to be our limits of integration. They're going to be x equals 0 to x equals 1. And now we're putting in our area of our washers, which we came up with this formula for, pi times x minus x to the fourth. And here I'm just going to put a little dot dot dot. This is not too bad of an integral. You should end up with 3 pi over 10. Okay, so that's example 4. We'll cover example 5 in the next part. Thanks for watching.